The first time I heard the name Jean-Christophe Yoccoz, I remember that very well. It was a Sunday afternoon in the middle of the 80s. I haven't really been able to check up the date, but it's probably 85, could be some year nearby. It was in Oberwolfach, that's why I remember it, and it was Sunday afternoon, just before the workshop, which was organized by Jürgen Moser and Eddie Sender at that time. It started 81, and so this may have been the third time or something like that, and it has gone on for every second year since then with other organizers, in particular Jean-Christophe. Moser usually arrived early on Sunday before the conference, and I also arrived early, and there were not many people. Usually he was quite occupied, but these times were somewhat precious because he didn't really have much to do, and we were sitting down talking nicely in the afternoon in Oberwolfach about different things, and in particular about the upcoming workshop. So as usual, there were a lot of names which nobody knew about. Young mathematicians with their future in front of them, but usually completely unknown, like myself. And then there was all these famous names whose works we had studied and who we had met at different conferences. Jacob Pallis was quite frequently there at that period, and there were a lot of other names, so I shall not mention. So we were discussing this, we were looking at their proposed talks and thinking about what will come up. And then, of course, Moser said, of course, Michel Herman will come from Paris, and he will bring Yoccoz. Yoccoz, I thought, what's that? Never heard the name. But I realized that since Moser mentioned him, he was not just a nobody like many of us. So I asked Moser, Yoccoz, who is that? He's a wizard. That was my first impression, the first meeting with Jean-Christophe that I heard, and I always remember this. So at that year, I was talking about KM theory, and I will have been continue with that, and I will talk about KM theory today also. Something has gone wrong here. At that period I was talking about nonlinear Hamiltonian systems, and today I will talk about linear Hamiltonian systems, which is in infinite dimension. It's a linear wave equation with quasi-periodic time dependence. So let me see if I can have this function. Yes. Okay. So here you see the equation. It's a second order linear equation, u double dot, two time derivatives, equal Laplacian of u plus m minus m times u plus a potential which is time dependent. X here is periodic, so it's a periodic boundary condition, and the time dependence which sits there is quasi-periodic. So more precisely, V is a function in d space dimension, periodic, and n angles. It should be real analytic, and it is evaluated over a straight line, t times omega, where omega is a Diophantine vector. So this, this gives me a linear wave equation or Klein-Gordon equation with a non-autonomous perturbation. V is supposed to be small here, and we measure it in some analytic soup norm. So this is perturbation theory. M is a mass parameter, and so we don't have just one equation, but as usual, we have a family of equations, and one would like to know what the solution looks like for this equation. Now, as usual, it's a second-order equation, so you can write it as a first-order one by introducing V as the derivative, and then it takes the form that is written up there. And by using a linear change of variable, you can diagonalize this autonomous part. The change of variable looks something like that. You introduce two new functions, psi and eta, instead of u and v. And then the equation in psi and eta takes this somewhat more symmetric form. So it's a diagonal operator here, which is non-autonomous. And then there is a perturbation f of tv, which comes from the potential, which is, has quasi-periodic time dependence. So this is what we call a quasi-periodic co-cycle in infinite dimension, and it's in fact a Hamiltonian one. So this operator here is J times a symmetric operator, and J is this standard complex symplectic structure. So this is the system we are interested in. Of course, when f is 0, everything is explicit and you can compute it, and now you like to perturb it. Another way to think about it is to introduce the Fourier coefficients of the function psi and eta. They are written as psi hat of A. A runs over the d-dimensional lattice, and eta hat of A, and then it becomes an infinite dimensional matrix system, which has a diagonal part here, diagonal matrix, and then some perturbation here. So it's an infinite dimensional symplectic quasi-periodic co-cycle we are interested in. And of course, when f is 0, we know everything about this. Before you like to say something about the solutions, you may ask, are there any solutions at all? And for this particular problem, there are. If you put yourself in an appropriate Sobolev space, H of S, where S is sufficiently large, or if you like to think about it in terms of Fourier coefficient, a weighted L2 space with weight 2s, S sufficiently large, then this system has a well-defined global flow, so the solutions exist well. And moreover, since it comes from a real system, remember that it is a real system, so it's written in complex coordinates, so it preserves this real subspace here. And what we are interested in this case is, do we have periodic solutions, quasi-periodic solutions, or almost periodic solutions for this system? Now, this is a perturbation problem with quasi-periodic solution. So let me come back to this, by the way. If you think about this, then you see if you ignore this term here, then everything can be solved explicitly. All solutions are, if you excite one mode, it becomes a periodic solution. If you excite finitely many modes, it becomes a quasi-periodic solution. And if you excite infinitely many modes, it will become an almost periodic solution. So all solutions of the unperturbed system here is almost periodic, and what we are interested in is if there are almost periodic solutions for the perturbed system also. That's the problem known as reducibility. Now, if you don't like PDEs or infinite dimensional system, you may just as well think about this as a large finite dimensional system. In that case, we know how to handle this problem in the perturbative setting. The problem is simply that if you have a large system of dimension n, then usually the perturbations that you can handle become smaller when n becomes larger. So if you like to treat this as a finite dimensional system, you can do it, but then the perturbation which you allow becomes smaller, the bigger is the system. And what we are interested here is to find something, to verify something which is independent of the dimension. So you can think about this as a large system, capital N times n, but we like to know something under a perturbation which is independent of this dimension. So this is just, you can just as well think about this as a finite dimensional system. Okay. So this is the problem. It's KM theory, and it's of course very much related to quasi-periodic solutions of the nonlinear wave equation, which has been studied quite a lot. It's not the same problem, but it's technically very much related. And I have written a bunch of names here of people who has been studying this problem for the nonlinear wave equation. Let me mention that most of these works, but not all, are in one space dimension. The dimension d equals 1. And for these kinds of problem, it usually makes a big difference when the dimension d, space dimension, is 1 or when it's higher. So there is a lot of works in one space dimension and relatively few works in higher space dimension. Here, most of these works are in one space dimension, but some of them, for example, Bourgain, is in higher space dimension. But that's usually much more complicated phenomena. Okay. So what do we want to do? Well, it's a dynamical system. So what you do in dynamical system is that you change variables. You conjugate your system, which is complicated, to something which is supposed to be somewhat more easier. And the conjugations that you do here, this is a fibered dynamical system. It lives on a base space, which is a torus, times a fiber. And what you want to have is fibered conjugations, which preserve this fibered structure. So you look at two linear Hamiltonian systems, and you like to conjugate them by a fibered perturbation. That amounts to constructing a matrix-valued or an operator-valued function here on the torus. And whenever you take a solution of the first system, C of t, then capital C of t omega times c gives you a solution of the other one, and vice versa. So this is a conjugation of two systems, and this is the way one should look at it. Another way to think about it is that such a conjugation is supposed to fulfill a system of linear PDEs on the torus. So here it is. You take your matrix here, you differentiate all matrix elements in the direction omega on the torus, and then it's supposed to verify j times a times c minus c j times b. So it's a linear system. So if these two are equivalent, these two notions of conjugations and solving this. The notion of reducibility is to say that the system is conjugated to a constant coefficient system, a constant cocycle, which has no explicit time dependence. Another way to state this is to say that the system is reducible if and only if its conjugation class contains a constant cocycle. Reducibility is a nonlinear problem, by the way. If you come back here, you have a system A, you like to conjugate it to a constant coefficient system B, but you don't know B. Huh? So you like to solve this equation, find J of A, which is given, unknown is C, unknown is B. So in that case, it becomes a nonlinear system of PDEs. So reducibility is a nonlinear system problem. Now, there is a weaker notion of reducibility, which is called almost reducibility, which is somewhat vague in its definition. Instead of saying that the conjugation class of the system contains a constant cocycle, you'd say that its closure contains a constant cocycle. The closure in some topology, which is, could be different for different systems. Huh? So that means that you cannot conjugate your system to a constant cocycle, but you can conjugate it as close as you wish to a constant cocycle. Huh? This is not the same as saying that the system belongs to the closure of the conjugation class of a constant cocycles. These two are different, but in fact, in most cases when we are able to prove this, in fact, we have both of them. Huh? So this is the question of almost reducibility. Now, what can we say about the linear wave equation, which I did mention? Well, in order to handle that, one needs a second Diophantine condition, which is different from the first one. It's a quadratic Diophantine condition. And how do you define it? Well, you take d linearly independent vectors in your lattice, and you take d vectors in the lattice C of n, Fourier modes. Take d Fourier modes, you take d linearly independent space modes, you take d Fourier modes, and you cook up this d by d symmetric matrix, which is kj times omega, ki times omega minus ij ia. That's just the usual scalar product here. So this gives you a polynomial which depends quadratically on omega. And you look at the determinant of this polynomial. This matrix, so a priori, it's a polynomial in omega of degree 2d. If you make the computation, you will see that it's in fact a quadratic polynomial. So this is a quadratic polynomial. When you vary e and k, it will give you a dense set of numbers, and you like to stay away from 0 for this number. So the only possibilities for this number to become small is when either e or k are very large. Huh? So that's a Diophantine condition, and it's not very hard to verify that if the exponent that you put here is big enough, then this set is non-void when kappa is small, and when kappa goes to 0, it becomes a set of total measure. So there is a lot of vectors omega that verifies this condition, this quadratic. This has been used before in the study of quasi-periodic solutions for the nonlinear wave equation. It may be Björgen who has used it the first, but I'm not sure. I know that it's in his book in any case. So there are two Diophantine conditions in this. There is the standard one, which we all know about, and then there is this one, which is adapted to the wave equation. Now, before I give you the result, let me give you some notations before that. So one will consider partitions of the lattice C of D. Huh? So you have a partition, which I call P here, and the diameter of this partition is the maximal diameter of all the partition elements here. Huh? There is in this kind of problem another diameter which is interesting, and that is what we call the radial diameter, which which is the supremum of norm of B minus norm of A when B runs over all the partition elements. That's the radial diameter, and then there is a normalized version of this. So maybe I shall just write a small drawing here. So if you look at the two-dimensional lattice and you look at the sphere here, then you may have a partition element which looks something like that, and you see that the diameter of this partition element is of this size. And then you may have another partition element which looks like something like that, and they have the same diameter. But the radial diameter is not the same, because the radial diameter here is big, while the radial diameter here is small. And the difference of these two are important in diffusion, because if you look on a weighted L2 norm and you move the mass from that point to that point, the weighted L2 norm will increase. On the other hand, if you move it from that point to that point, the weighted L2 norm will not increase. So they will have different function in diffusion, this one. It's not really, if you are interested in diffusion, it's not really the diameter of the partition elements which is interesting, but mostly the radial diameter. So once you have a partition element, you can have a projector associated with it. So instead of looking at the Fourier coefficient or all Fourier coefficient of U, you take just out the trigonometric polynomial of the Fourier coefficients where each element lies in the partition elements. And if you have an operator here or a big matrix, then you say that it's block diagonal over the partition, a partition P, if it can be written simply in this way. So it means precisely modulo a permutation of the base element, a block diagonal matrix, is precisely what we usually think of as a block diagonal matrix. So if you just have a matrix like that, you make a perturbation of the basis elements, then you will be able to write it as a block diagonal matrix. And the diameter of the blocks will, of the partition elements, will give you some control on the sizes of this block. So if the diameter is small, the block dimensions cannot be very large. So this is a block diagonal matrix, and of course you see that if the block has finite dimensions, if the partition has a finite diameter, a block diagonal matrix is just a direct sum of finite dimensional matrices. So in principle you know everything. Yes?
What's the meaning of the denominator, the magnitude of A?
The meaning here? Well, it's just if you look at, it's just a normalization. So if you look on another block here, which looks farther away, you just normalize it to be the size.
But doesn't the magnitude of A depend on the representative of the block?
Yeah, sure. You take the maximum. I think you take the maximum. Yeah, well, you take the maximum. Really doesn't matter. You take the maximum over all A's in the particular block. A here, the block is well defined, but its element is not well defined, so you take the maximum overall. Doesn't really matter for this problem. Okay. So now I think I can give you the result about this wave equation, and it says that if you have an omega which verifies the usual Diophantine condition plus the quadratic Diophantine condition, which I mentioned. Now, if the perturbation is sufficiently small in some analytic norms, then there exists a subset of masses m. Remember that our system depends on the mass parameter m. So there exists a set of good masses m, which is big in measure sense, such that for all good masses, the co-cycle is almost reducible. More precisely, there is, of course, a quantitative version of this. So more precisely, it tells you the following. You have a perturbation which is of size epsilon. Now you take any epsilon prime, whatever size it is, and then for any epsilon prime, there exists a partition, there exists a conjugation, there exists a partition P, which depends on epsilon prime, there exists a conjugation C, which conjugates our co-cycle to this particular form. And the autonomous part is block diagonal, symmetric block diagonal over this partition, so the blocks may be pretty big, and the new perturbation f prime is smaller than epsilon prime. So you can conjugate it as close to a constant coefficient system as you ever wish. The problem, the cost here is that you start with a diagonal system. Now it's no longer diagonal, it's block diagonal, and the blocks are pretty big, but not too big. The diameter of the blocks is log of epsilon prime, absolute value, and the normalized, the radial diameter is log of epsilon prime. Also, the conjugation here, it is symplectic, bijective, etc., and it becomes pretty large. When epsilon prime is small, it becomes pretty large together with its inverse, but not too large. It becomes log of epsilon prime, and the perturbation, you are epsilon prime close to a constant coefficient system. So this is what you can prove. Now, what can you use such a statement for? Well, everything in this, formally, if you have a reducible system, you conjugate it to constant coefficient system, then you know that all solutions are almost periodic, and you will have also growth on infinite time for the solutions in Sobolev norms. So that's usually what is called localization. Now, if you have almost reducibility, then you also only have approximations of your solution by almost periodic functions, and you have growth on finite times. Now, in general, this does not say so much. I mean, any function can be approximated by an almost periodic function in finite time. So everything that comes in here comes from the estimates. And so here are the estimates, which tells you the diameter, the radial diameter, the size of the conjugation, and closeness to constant coefficient. What kind of estimates can you do for this? Well, here is one example of what you can get for these kinds of estimates. So if you take good mass m, then all solutions of this particular wave equation satisfies a bound which is log of t. It's not bounded, but to be non-bounded, it is pretty bounded. So log of t, and that comes, of course, from the fact that the radial diameter here is of size log of epsilon prime. So it's essentially an easy computation type Gronval or something like that. So this is the kind of estimates you can do with this kind of stuff. Let me also mention another one, because this theorem is valid not only for the linear wave equation, but for much more other perturbations of this unperturbed co-cycle. And with this statement, you can solve, if you like to do KM theory, you can solve the homological equations with pretty much accuracy. This is a way to use it. So this is what is known here. So let me see what time is I have here. Okay, so that's the best I can do. I cannot prove reducibility for this particular problem, but only almost reducibility. Let me mention another problem which we have solved with Sergei Kuksin some years ago, where we got a better result, and that was for the linear Schrödinger equation. So you have a linear Schrödinger equation, u dot equals I times delta times u, and you make a perturbation, a non-autonomous perturbation, which is quasi-periodic in time. No, that goes in the... in this problem, we don't have any mass parameter, but we use the frequencies omega as parameters. So for any choice of omega, here we have one equation, and you can write it as a system, an infinite dimensional unitary quasi-periodic co-cycle written in Fourier coefficient. Yeah.
The potential is multiplicative, not convolution.
No, it's a multiplicative potential. Convolution becomes much easier. Yeah. No, it's a multiplicative potential. So what did we prove for this thing? Well, we proved that if the potential is sufficiently small, then there exists a big subset of good frequencies such that the corresponding co-cycle for these good frequencies is reducible. In this case, one has much more control. There is a conjugation which is unitary and, in fact, which is close to the identity. And it conjugates this now to a constant coefficient co-cycle, which is block diagonal with finite dimensional blocks. So in this case, you have much stronger conclusions here. All solutions of these systems are now almost periodic, and you have control you have boundedness in the Sobolev norms for the solution. It's even better than this because it tells you that the norm of ut minus the norm of u0 is small. So this is what one can prove for the quasi-periodic Schrödinger equation. And to come back here once again, complete reducibility with a transformation that is really close to the identity, and finite dimensional blocks, while for our system here, we have not complete reducibility, we have not transformations which are close to the identity, and we have a block decomposition which becomes a priori bigger and bigger. So it's a much weaker result, but that's the best thing we can do. Let me see what time I have. Okay. So let me mention here what one could hope for. What we know in the case of finite dimensional systems. In finite dimensional system, we know much more. So if you look at the finite dimensional quasi-periodic co-cycle here, omega is Diophantine. You can write it in this way as a non-autonomous linear system, or in this way as a co-cycle. As a skew product flow. And omega is Diophantine. A is a matrix-valued function. I don't know if I said that it's analytic, but I will say it's so. So it could be in the general linear group or algebra, but it could also belong to some sub-algebra. The case that is most studied is the second-order Schrödinger equation, stationary. In this case, it becomes a cocycle in SL2R when E is real, and in SL2C when E is complex. So what do we know about this system? Well, we know the following. So let me just remind you what was the reducibility. There should exist a fibered conjugation of this cocycle which reduces this to a constant coefficient cocycle B. So that's the kind of nonlinear equation on the torus which you like to solve. And in this case, when you can conjugate it to a constant cocycle, you get an explicit expression for the solutions, which is given by the solutions of a constant cocycle times a quasi-periodic time dependence. And if you take eigenvalues of B, eigenvector and eigenvalues, this will give you what is usually called Floquet solutions of this system. Huh? The reducibility is what this is about. Now, what can you prove for this kind of systems? Well, suppose you have a one-parameter system like that. Y dot equals lambda of A plus f of phi. F is an analytic function on the torus, omega is Diophantine, and lambda is a parameter on the torus. Then what we can prove, or know about this, is that for a generic A, then the system is almost reducible for all parameter values, and it is reducible for almost all parameter values. So this is what we know in finite dimension. In infinite dimension, the examples which I gave you are much weaker. For the Schrödinger equation, we get reducibility for a large set of omega, but not for a large set of the parameters, but not for almost all parameters. And for the wave equation, we get almost reducibility for a large set of parameters, but not for almost all, and certainly not for all. Huh? So one could ask the question, yes?
Do you know something about the Hausdorff dimension of the complement?
The Hausdorff dimension of the complement. Between what? Of the non...
Yes.
Of the non-reducible one.
Yeah.
Yeah. So first of all, there are non-reducible ones. Yeah. Yeah. And what is said here is that they are of measure 0. Yeah. I'm not really sure, but my guess is Hausdorff dimension 0. That's what I would guess. That's what I would guess. Yeah. But as Matteo says, that so there are examples where we proved you that. In fact, it's not reducible for all lambda. Everything tells us that generically, in a topological sense, the generic system is non-reducible. So there is a difference between this. But for infinite dimensional systems, like the wave equation, you could ask if such a statement is true. I have no idea. I have no idea. And what we can prove is something that is much more weaker, but still something. Okay. So, yeah. Okay. So I think I shall just say a few words about what is the difference and why we only get almost reducibility for the wave equation, why we get reducibility for the Schrödinger equation. There is one answer to this which is completely wrong, and that is that you may say that for the Schrödinger equation, I have much more parameters here. Huh? I take omega, which are an n-dimensional vector, huh? And I work with that one, while for the wave equation, don't use omega as a parameter. I used m. I just have one parameter. Huh? And you may say, maybe if you use omega as a parameter, you have much more freedom. Huh? And the answer to that is, well, you have much more freedom, but I mean, you cannot do anything. Huh? I cannot prove the same result here for the wave equation with omega as a parameter as with m. In fact, the appearance of the parameter in the eigenvalues is very essential. And for this problem, m, I can handle m as a good parameter. I cannot replace m, fix m, and use omega as a parameter. The problem of the parameters are they are not equivalent. They are really play different roles, and so it's not really the choice of parameters that makes the difference between these two problems. It's the eigenvalues which makes the difference. So let me just mention what the eigenvalues looks like. So suppose you have a diagonal matrix, finite dimensional or infinite dimensional, written here, I times lambda A are the eigenvalues, and you like to perturb it by a matrix which is time dependent, f of phi. In all these problems, it's natural to have decay of these matrix elements in terms of the Fourier coefficient and decay in exponential decay of the diagonal in the space mode. And that comes from the fact that you take simply an analytic potential. If you don't have an analytic potential, you will have weaker decay, but this is complicated enough. So you like to consider a matrix like that, diagonal, perturb it by something time dependent, which has some decay off diagonal and some decay, exponential decay in Fourier modes. Now, what you like to solve is this equation. This is my system, my cocycle. I would like to conjugate it to a constant cocycle A prime by a conjugation, which is capital C. So what you do is, of course, that you think that capital C, when epsilon is 0, you can solve it explicitly. So you think that it should be something which is close to the identity. So you write C in this form. You write A prime as A plus epsilon B. You linearize the equation, and what you get for C, that is for x, you get the linear operator, which is going to be that one. And that one is you like to solve, and you like to solve it not exactly, but only mod epsilon, because in any case it's an approximation. So now what comes in here is to study the eigenvalues of this operator. And these eigenvalues looks like this. K omega coming from the differential with respect to omega, and eigenvalues here, lambda A, lambda B, are the eigenvalues of the matrix A. So you like to bound this operator, these eigenvalues. You like to invert this operator, so you don't need to control these eigenvalues. Now, the fact that you have truncation and you only like to solve it up to a certain approximation means that you can truncate this system completely into finite dimension, basically. You truncate it in Fourier modes. Don't need to consider higher Fourier modes than log 1 over epsilon, and you truncate it off the diagonal in the space mode. And in order to invert it now, you need to have something which is called, in this theory, called the second Melnikov condition. So you like to have a bound, lower bound, on these eigenvalues for all Fourier modes and all space modes of the diagonal. Well, that you cannot have. In general, you have to exclude at least A equals B when the two eigenvalues are equal, and K 0, because in that case it's 0. But otherwise, you may hope to solve this for some delta, which should be small, but not too small. This is what you usually like to do. Okay, so can you do it? Well, for the Schrödinger equation, the eigenvalues are integers. Norm of a square, they are integers. And when you perturb it, they are perturbations of integers. And you can prove, in fact, that this, what we call the second Melnikov condition, is fulfilled for a large set of omega. So you can solve the linearized equation for a large set of omega, and etc., etc., etc. UKM theory. For the wave equation, the situation is completely different. The eigenvalues are no longer integers, but they are square root of integers. So basically, they are dense. And the fact is that the second Melnikov condition is always violated. It is always violated. For any choice of m, and if you like to use omega as a parameter, it doesn't help you. So they are always violated. So this is the complication. You cannot really solve perturbatively the linearized equation. Now let me just finish this. I think I'll finish this by saying that how do you handle this kind of problem? Well, the way you handle it is that you have to analyze all the violations of this guy. So I must describe all the violations of the second Melnikov condition, and then you can make a change of variable which reduces these violations to the violations A equals B and K equals 0. In fact, the explanation is that the eigenvalues of this operator are not invariant under conjugations. When you conjugate your system, you change the eigenvalue. And these are usually, you have to do conjugations which are non-homotopic to the identity. Then you can change the eigenvalues. And what you do is basically that you change the eigenvalues of this one so that all the violations that occurs here, in fact, will be, after change of variable, will be only this one. But that requires that you use transformations which are not close to the identity. And if you use transformations which are not close to identity and you like to iterate such a construction, you have no guarantee at all that things will converge. And that's why you only get almost reducibility instead of reducibility in this case. So this is reducibility for this problem is an open question. So I don't think I like to say anything more about this. I still have some time, but I think I will stop there. Okay, thanks for your attention.